Okay, this question is a particle moving on the inside of a hollow hemisphere. It says it's a smooth surface, so the inner surface is smooth, fixed hollow hemisphere, centre naught, which is up there, radius is 5. So this is going around the particle, constant angular speed, omega, horizontal circle, at a vertical distance of 3 meters below the level of O. So the fact that it says both horizontal and vertical, both in the same sentence, is potentially a bit confusing. But of course, what it's saying here is with the vertical distance of 3 meters below, it is just a description, a verbal description of that distance there. So that is where the particle is kind of going around on the inside there. Question 7 this time. So you can see, the total number of marks, 3 plus 4, and a huge 8 for the last part. So this, in the old style exams, was deemed to be one of the trickiest ones there, which is why I've chosen this one. Okay, so to start with, let's cover that up. We have got to find the magnitude of the force exerted by the hemisphere on P. So it makes it sound really complicated, but that is just another way of saying the reaction force. So we have a reaction force whenever something is acting on a surface, and this reaction force is what the hemisphere is doing to the particle. Whenever you have a normal reaction force, of course, it occurs perpendicularly to the surface. So if you imagine a tangent there, we would have that normal reaction going in that direction. And of course, I've missed, but we know that the radius and the tangent are perpendicular, so it needs to go a little bit more like that. But of course, that is important because we can now work out what these angles are. If I call that theta, and I'm just going to draw this triangle out here, there is our right angle. Of course, it's not explicitly said, but because it's a radius of 5, that length there is the same as that length there. So, of course, it's a little bit hidden. That is the angle I'm going to find. And you will, I'm sure you're already aware, an awful lot of 3, 4, 5 triangles. 5 squared minus 3 squared, of course, is 4 squared. So that means that if we are asked to work out sine theta opposite 4 divided by hypotenuse 5, if we need to work out cos adjacent 3 hypotenuse 5. So rather than finding the angle and using decimals, using those is much easier. Okay, so I know I've got this diagram here, but I'm just going to draw out again what's going on with P. We've got the weight acting vertically downwards, and then we have our normal reaction force there, and that is acting at an angle of theta. I'm going to look at what's going on in that direction there. In that direction there, it's in equilibrium. It's always in equilibrium. So forces up equal forces down. That is the adjacent side, so it's going to be the cosine component. So I can say that R cos theta is equal to the only force going down, 0.2 g. So I don't have anything else at all happening in that direction. I further know that cos theta is equal to 3/5, so R multiplied by 3/5 is equal to 0.2 g. R is equal to 0.2 g over 3/5. Of course, that's 0.2 over 0.6, so it'll be g over 3, but, I suppose we're working with decimals, or we're allowed to in mechanics, so all right, that's 2 decimal places. Okay, now part 2, of course, we are looking at what's going on in this direction. So in that direction, we're not in equilibrium, we are using F equals ma. We got that acceleration acting towards the centre of the circle. And of course, the centre of the circle just means the centre of this horizontal circle. So I'm not going to be using 5, which is the radius of the hemisphere. I specifically want the radius that our particle is going round in. And that is this distance here in pink. So what I'm going to be using is, I've already worked it out there, it's that length 4. So I've got a 3, 4, 5 triangle there. So R is equal to 4. And we want omega, so we're going to be looking for our acceleration. A is equal to omega squared r. So in the direction of the acceleration then, and my acceleration is in this direction, I've got the other component of r, which is going to be r sine, so it's going to be that component there. It's opposite the angle. So r sine theta is equal to the mass 0.2 multiplied by omega squared mr. R multiplied by sine theta. Actually, we know r, don't we? The 3.27 or the g over 3. Sine theta, I've got up there, that's 4/5, is equal to 0.2 multiplied by omega squared multiplied by r, which is 4. Know everything there, we just need to work out omega squared. And of course, I am not liking my mixture of fractions and decimals, so that just is instinct. And of course, we could find exact values of things, but G, must remember, is just an approximation anyway. When you work through all of that, you do just end up with G over 3. Again, the 4s cancel, the 5ths cancel. So that would go, that would go, that would go, and you'd just be left with G over 3. 9.8 over 3, so it means that omega is equal to the square root 9.8 over 3, 1.81 radians per second. Okay, so that's quite standard. There shouldn't be anything too awkward there. But why is this last part of the question worth 8 marks? So we've now got an additional particle. This particle down here is 0.1 kilograms. It's attached with light inextensible string, of course, through a hole there. That mass is 0.1. That's hanging in equilibrium. So it's very similar to the first question that we looked at. P moves in the same horizontal circle as before. So actually, all the things that we had marked on there before are still going to be valid. So in particular, our normal reaction going in that direction there. So that's where R is going to be. So when we've got our angle of theta, just see what I had before. I had that sine theta was 4/5 and cos theta is equal to 3/5. Calculate the new angular speed. Well, I've got this new force, tension. So I've got my normal reaction force and I've got tension force. I need to obviously find what that tension force is. I can do that directly by looking to see what's happening on this additional mass here. So that's P, so shall I call this Q? So on Q, it's in equilibrium. we only have two forces. We've got our tension force and we've got our weight force. So T is equal to 0.1 G. T is equal to 0.98. I also then need to look and see what's happening on P. Now P, there's a lot more interest happening in P. I've got the weight force acting down and the weight of P is 0.2. So I've got 0.2 going down there. I've got my normal reaction force. And because it's happening in the same position as before, that value of theta is going to be the same. I'm just marking on my horizontal there. And then I've got this new tension force. I know what the value of the tension force is, but I need to kind of figure out this direction. So I'm going to put T in there. And my angle, well, it doesn't matter where I put it, I'm going to put it there relative to the horizontal, and I'm calling it alpha. Right, we need to look and see what's happening then on P. Vertically, it's in equilibrium. So that means that my R component, so that's the only force going up, is going to be equal to the two forces going down. So that's all of the weight and a component of the T. So if you look at this triangle here, you know, as we, I think, did in the first part, I need that component, and that component is adjacent. So I know up I've got R cos theta. Going down, I've got all of the weight force, and then I've got this component of the T. That component is opposite the angle, so that is the sine component. So T sine alpha. I know cos theta, that's 3/5. I know T, but I need to think about what this sine alpha is. So let's go back to this diagram here. So the way that I've marked out alpha, I've set alpha to be this angle here. I know that that's equal to 4. I need to work out what these other two sides are. Now, that length is 5. That means that this length all the way down here is also equal to 5. And that length is 3. So this has got to be the difference between the two. So I know that that length is equal to 2. So I've actually got now this triangle, and alpha is there. I've got that right angle, I've got 2, and I've got 4. So I know that this hypotenuse, 4 squared plus 2 squared, so that's going to be root 20 or 2 root 5. So for this triangle here, I know that sine alpha opposite over hypotenuse, 2 over 2 root 5, or 1 over root 5. And I know that cos alpha is adjacent over hypotenuse, 4 over 2 root 5. So that's going to be 2 over root 5. So that is just in addition, you know, to kind of the main body of what's going on there. So means in here, I know that R times by cos theta, which is 3/5, is equal to 0.2 multiplied by 9.8 plus T, which I know is 0.98 times sine alpha, which is 1 over root 5. So I know absolutely everything there, apart from R. So 0.2 multiplied by 9.8, I think that is equal to what, 1.96 plus 0.98 multiplied by 1 over root 5, all divided by 3/5 or 0.6. So that gets me 4.20. And I'm just going to check that because I'm looking at my previous answer. I'm not sure whether that is correct. So if I just type in all of that stuff on the right, well, 4.2, yeah, that's right. Okay, so we're nearly there. We now just need to look at what's going on horizontally. So I've looked at that vertical direction, looking at it horizontally. Of course, now I've got two forces going in the direction of the acceleration. So this is towards the centre. I'm going to have the other component of R. It's the sine component. I use cosine there. So R sine theta. I've got the other component of the tension. I use sine there, so it's going to be cos, and of course it will be cos because that's the adjacent. So plus T cos alpha, and that is equal to m times by the acceleration, because it's angular speed, omega squared r. So I've got r, which is 4.20, multiplied by sine theta, which is that 4/5 there, plus t all the way up there, 0.98, multiplied by cos alpha. Cos alpha is this one here, 2 over root 5. And that is equal to the mass of it, which is 0.2 times by omega squared times by r. Just be careful with r. The radius is 4. Yes, it's that length there, the 4. And again, we know everything apart from omega. So we just need to sort out all of that. So 4.20 multiplied by 0.8. And then I've got 0.98 multiplied by 2 over root 5. And I've got the 0.2 and the 4. So that'll be 0.8. Working out that gets 5.096. So finally then I just need to square root. And whoops, 2.26 radians per second. So if you look at that, even though that was worth, I think it was 8 marks, it's really just the same process as you've been doing in the previous 2 questions. It just broke it down for you. So you look at the simpler particle, generally work out the tension because they'll be attached. You then look at the one that's moving, always resolve vertically first because it's in equilibrium. Work out the values of the sine and cos separately. Keep to exact values. You don't want to be dealing with an angle where you've got decimals in. From your vertical motion, you'll either have an equation with 2 unknowns, or you'll actually have been able to work out one of the specific forces, which we could do here. Then look at what's going on in the direction of the acceleration. Use F equals ma. Either omega squared r or v squared over r to find your velocity.